All right, let's take a look at some of these practice problems for the Q2 exam. And again, this is focusing on the non-programming aspects. So that basically means like logic, gates, circuits, and then computer components. All right, number 1 here. Assume that A is true, B is false, and C is true. Evaluate the expression below, showing your work. All right, so from the problem, they're telling us that A is true. They're telling us that B is false. So there's another false. And then they're telling us that C is true. All right, so if we have a true and a false, that's going to give us a false. But then that false is being negated. So that's eventually going to give us a true. All right, then we have and here. This is just a false or a true. All right, with an or, we only need one of them to be true. So we know this is true. And then we're left with true and true, which means the whole thing is going to be true. All right, so just being able to plug in falses and trues and then evaluate them by looking at the ands, the ors, and the nots. Number 2, draw a circuit corresponding to the following Boolean expression. Your circuit should match the expression by using the same number and types of Boolean operations. So that means we're not simplifying it at all. So if I have 2 plus signs, I'm going to have 2 OR gates. If I have 2 negations, I'm going to have 2 NOT gates. And if I have one kind of multiplication here, I'm going to have 1 AND gate. But there should be kind of a direct correspondence between what's going on in this expression and the circuit that I draw. Okay. So with this one, I'm not going to do the vertical lines on this one because it's not as involved. I'm just going to kind of go in and just kind of get started on this. So I'm going to make this line A, and I'm going to have A feed into an OR gate. So there's my OR gate. So I'm kind of representing this part right here. Now this is B not, so I'm going to have my line for B, but then I'm going to have it feed into a NOT gate and then feed into the OR. All right, so far I've taken care of this part right here. All right, now I'm going to take advantage of this part right here. So this is just A and C feeding into an AND gate. So let me draw my AND gate. There's my C. I'm going to have that go in right there. I'm going to draw a dot here and then show that it's going over and going into the AND gate. So I've taken care of that part right there. These two parts are being ORed together. So I'm going to have both of these feed into an OR gate. So there's my OR gate. So I've taken care of now all of this. And then the last piece is that this whole expression is being negated. So this OR gate is going to feed into a NOT gate, and that's going to give me the complete circuit. All right, so notice there were 2 negations. I have 2 NOT gates. There were 2 plus signs. I have 2 OR gates. There was 1 multiplication happening. I have 1 AND gate. So everything kind of matches up. All right, number 3, write a Boolean expression and create a truth table corresponding to the circuit below. Your expression should match the circuit by using the same number and types of Boolean operations. So basically, the flip of this. This one, we gave you the expression and you had to draw the circuit. Now we're giving the circuit and you have to draw the expression. All right, so we can kind of see that we have A and B feeding into this OR gate. So we know that we're going to have an A plus B. So I'm going to just start by writing my A plus B. Then I have a B and a C not feeding into an AND gate. So I'm going to write this right here, B, C not, right next to each other. then both of these feed into an AND gate, which means that this piece is going to end up getting multiplied by this piece. So I've got A plus B being ANDed together with B times C naught. All right, here's the B times C naught. Here's the A plus B. Those are both feeding into an AND gate, which is multiplication. And then the result of that is being negated. So I'm going to put an extra set of parentheses around this whole thing and then throw a negation on the outside there. All right, so that's kind of going in the other direction. Now, if I'm going to make a truth table, I'm going to start with the three inputs. So my three inputs are A, B, and C. Now, what I want to do is list out every combination for A, B, and C. So the way I start by doing that is I start with 4 zeros, because there's going to be 8 rows in total. And then I go 0, 0, 1, 1, 0, 1, 0, 1. All right. That runs through all the combinations where A is 0. Also, it happens to be counting in binary, all right? In binary, that's 0. In binary, that's 1. In binary, that's 2. In binary, that's 3. In binary, this would be 4. But again, I'm basically just repeating it and now doing all of the combinations where A is 1. So I'm going to do 0, 0, 1, 1, and then 0, 1, 0, 1. Now, when you're making this truth table, the only requirement is that you show me all the inputs, which I've already done, and you show me the final output. But trying to do everything in your head can be really difficult. So you can put as many intermediary columns in there as you want. That's up to you. So I could put in a column for C naught. I could put in a column for A plus B. I could put in a column for B times C naught. I could put in a column for A plus B times B C naught. And then I could put in a column for the final output. But you always need to have one that represents the final output. And again, the output for this one, we already wrote the expression, is this right here. But that would be the final output. Okay? So C naught is just going to be the reverse of C. So 1, 0, 1, 0, 1, 0, 1, 0. A plus B. Remember, with an OR, only one of them has to be true. So the only time this is going to be false is when they're both zeros. So that first two, they're both zeros. Then we have a 1, then we have a 1, then we have a 1 over here, a 1 over here, and then double ones there. Okay. Now, this is B and C naught, and is only true when they're both true. So using these two columns here, they both have to have ones, otherwise this column is going to be a 0. So there's one where they both have ones. Back to just only one of them having a 1. Only one of them has a 1. They're both zeros on that one. There's another one where they're both 1. And then there's only 1 1 there. So when we AND those together, it would be 0. All right. Now we're ANDing together these two columns. So again, we're looking for columns where they are both 1. So right here is no good. Right here is no good. That one would work. Right here is no good. No good. No good. That one would work. No good. All right. Now the output is just this expression being negated. So basically all the places I have zeros, I'm going to flip them to ones. All the places I have ones, I'm going to flip them to zeros. All right. So this would be the output. These would be your inputs. So the inputs and the outputs are all that are required. But if you make a mistake and there's no work to show me, you're going to lose a lot more credit. So I would recommend that you do these intermediary columns so that if I see a small mistake in one of these columns, I can be like, oh, okay, that was just a tiny mistake. I don't really need to take off much. Versus if you skip all the way to the output and there's something wrong, I have to take off a lot more because you didn't show me any of these intermediary columns. So again, up to you how much you do with these like middle 1, 2, 3, 4 columns here. But you are required to have all the inputs and the final output when you're making one of these. All right. Again, I would do more, but that is sort of the bare minimum that's required. All right, number 4, design a circuit using the sum of products algorithm that implements the following truth table. For full credit, you must show the results of each step of the algorithm, including the final equivalent Boolean expression for this truth table. All right, so I've been telling you since day 1 you were going to have one of these problems, so no reason not to practice. But what do we have here? So we start by identifying the rows with ones. So we've got a row here, we've got a row here, we've got a row here, and we've got a row here. All right, so that's step 1. We've identified the rows with a 1. Then we write out the expression for that individual row. So when there's a 0, we write it as A naught, B naught, and then when there's a 1, we just write the C. So that line would be A naught, B naught, C. This one would be A naught, B, C. This one would be A, B naught, C naught. And then this one, since they're all 1s, would just be A, B, C. I think I goofed something up when I was making my table here, because usually I would make that the bottom row, not the top, not the second bottom row. So I apologize for that. They're in the wrong order there, but it is the correct row that has a 1 there. So that should be A, B, C. Let's see. So now that we have our 4 expressions, all right, we want to write that as one complete Boolean expression. So we take these 4 individual pieces and we just OR them together. So it would be A naught, B naught, C plus A naught, B, C plus A, B naught, C naught plus A, B, C. All right, so this is kind of step 1. This is step 2. This is step 3. And then step 4 is drawing the actual circuit diagram. All right, and with one of these, I'm definitely going to use the vertical line trick. So this is going to be A, and then we're going to have our A naught. Then we're going to have B, and then we're going to have our B naught line, and then we're going to have C, and then we're going to have our C naught line. And as we've talked about before, the gates usually only have 2 inputs, but I don't need you to like string multiple gates together. We can just have them all going into 1. So this first one says A naught, B naught, C. So what we can do is we can have an AND gate that just takes in 3 inputs. So we're going to say A naught, B naught, and then C. And we'll do the same thing for all of these. So we'll get our 4 AND gates, and we're just going to have each of them take in 3 inputs. So the next one's A naught, B, C. So there's our A naught. There's our B. There's our C. The next one's A, B naught, C naught. So again, there's our A. There's our B naught. There's our C naught. And then the last one is just ABC. So A, B, and C. All right. And then the same thing, technically OR gates aren't really going to usually have 4 inputs, but we're just going to have them all going into one OR gate because we kind of understand what's happening here. So, all right, it's not wrong if you string together OR gates, like have these two go into one gate, have these two go into a different gate, and then have those feed into a third OR gate, but we're just going to simplify it and have all 4 of these go into a single OR gate. And that's our final output there. All right, so this is the sum of products algorithm, and I can pretty much guarantee you this is going to show up on the test. So you start by identifying the rows that have ones. Then you write the expressions for those individual rows. Then you write the combined expression where they're all being ORed together. And then you use that combined expression to draw your diagram. And again, when you're drawing these diagrams, I think this ABC method where you use the vertical lines and you have the knots and you just kind of tap into each of those lines is the neatest, most organized way to do it. If you try to do it like we did on the front here, it can get really messy and really hard to follow. So when you are doing a more complicated or more involved circuit diagram, I would strongly recommend that you use this technique right here. All right. So this is a lot of what you need to know for logic, gates, and circuits, in addition to just like the basic kind of vocabulary surrounding the topic. All right. Now let's flip over and look at some of the stuff that you might need to be able to do for the computer components section. All right. So there's definitely going to be a question where I give you information about a hard drive. And then you have to answer all sorts of questions related to that. So let's look at an example here. Consider a hard drive consisting of 4 platters. The platters are double-sided, meaning you can store data on the top and the bottom of the surface. Each surface contains 50,000 tracks, each divided into 650 sectors. Each sector can hold 1,024 bytes of data. All right, the platter rotates at a speed of 7,200 RPMs. The track-to-track, our movement time is 0.01 milliseconds. So that's kind of the rundown of our hard drive. Now we're going to ask a series of questions that revolve around it. So number 1, what is the maximum amount of data that can be stored on the entire drive, including all platters and sides? Express your answer in both bytes and gigabytes. Show your work. All right, so we have 4 platters that each have 2 sides. All right, so that basically means we have 8 surfaces. On those 8 surfaces, there are 50,000 tracks. So if we do 8 times 50,000, that tells us the total number of tracks. Each of those tracks is divided into 650 sectors. All right, so this was 50,000 tracks times 650 sectors. That will tell us the total number of sectors across all the tracks. And then if they're telling us that each track can hold 1,024 bytes of data, all right, that will let us know the total amount that is stored on the hard drive. All right, so on this one, we've got 4. Oops, it's kind of hard to see this. 4 times 2 times the 50,000 tracks times the 650 sectors times the 1,024 bytes. Now on this one, you're getting an answer that's in scientific notation because it's so large. You're not going to need to worry about that as much on the test, but be aware that that is scientific notation. So that's 2.6624. And then e to the 11th power. So that means there's going to be a whole lot of zeros that are coming after that. All right, so that's going to be 2, 6, 6, 2, 4, and then 6 zeros. All right. So in total, 26,624,000,000 bytes. Now it says express your answer in both bytes and gigabytes. So this right here is in bytes. And then what you need to remember is you can either divide this number by 2 to the 20th, or you can kind of do it step by step and say, okay, well, 1 megabyte has 1,024 bytes, and 1 gigabyte has 1,024. Whoops, I skipped one. Sorry. Because you're not dividing by 2 to the 20. That would be megabytes. 2 to the 30 for gigabytes. So 1,024 bytes in a kilobyte. My apologies. 1,024 kilobytes in a megabyte, and 1,024 megabytes in a gigabyte. So you're actually dividing by 2 to the 30th. All right, there are 2 to the 30 bytes in a gigabyte. There are 2 to the 20 bytes in a megabyte. There are 2 to the 10 bytes in a kilobyte. So I skipped one there. So you can either just divide this number by 2 to the 30th, or you can go through this process of saying, okay, 1 kilobyte is 1,024 bytes. 1 megabyte is 1,024 kilobytes. 1 gigabyte is 1,024 megabytes. Either way, when you multiply these numbers together, that's the same as 2 to the 30th. So you're still dividing this number at the end of the day by 2 to the 30th power. And when you do that, you're going to get 247.9532223. So all of this is going to equal 247 point, we'll go to 2 decimal points, 96 gigabytes. All right. But basically, you're using the information about the number of platters, whether they're dual-sided, how many tracks they have, how many sectors they have, how much data is in each section or sector, figuring out the total size, which is right here, and then converting it to whatever it asks you to convert it to, whether that's kilobytes, megabytes, gigabytes, or terabytes. And again, if it was terabytes, it would just be 1 terabyte is 1,024 gigabytes. And you just keep going using that scale of 1,024. All right, number 2, what is the time that it takes the drive to make 1 full rotation? All right, so we know that it makes 7,200 rotations in a minute. We want to know how long does it take to make 1 rotation. All right, so we can start with another fraction here and say, all right, in 1 minute, it makes 7,200 rotations. All right, well, we know there are 60 seconds in 1 minute. And hopefully we know there are 1,000 milliseconds in 1 second. So if we kind of go through here, we can say, all right, these are going to cancel out, these are going to cancel out, and we're left with 60,000 milliseconds for 7,200 rotations. All right, and this top part of 60,000, it's always going to be 60,000 for these because there's always a 60,000 milliseconds in 1 minute. So I'm going through and showing you the work here, but basically this 1 minute is always 60,000 milliseconds. And then we're just seeing, all right, if you can do 7,200 rotations in 60,000 milliseconds, and we divide these two numbers, 60,000 milliseconds is enough to get 7,200 rotations. That means each rotation is taking 8.33 milliseconds per rotation. So one rotation is taking 8.33 milliseconds, which is why we can do 7,200 rotations in a minute or 60,000 milliseconds. So again, when you're getting these speeds here, you can go through each of these steps, or you just have to remember that there's 60,000 milliseconds in a minute, and then just do that divided by the number of rotations. And that's giving us the rotational speed. All right. Now, using this rotational speed, we can figure out the best case, worst case, and average case for hard drive access time. All right. So we start with the seek time, which is the amount of time it takes the arm to move to the correct track. Now, in the best case scenario, the arm is already on the right track, so the seek time will be 0. Latency is the time for the disk to spin so that the start of your sector is under the read-write head. Again, in a best case scenario, the disk will already be in the right position, so there will be no latency. All right. Now, the transfer time is the amount of time it takes to read the data. All right. That can never be 0, right, because it always takes time to read the data. But basically, you're saying to yourself, okay, each track is broken up into 650 sectors. It takes 8.33 milliseconds to go around and read an entire track, or all 650 sectors. So to read just one sector, it's this 8.33 milliseconds divided by the 650 sectors. And that will give you the time to read just a single sector. So if we take this 8.333 from before and we divide it by 650, we end up with 0.0128. 0.0128 milliseconds. And again, in this one, the total is easy because those were both 0. So we're just left with 0.0128 milliseconds. All right, now, worst case scenario, when you're talking about seek time, would be that if the arm is on the outermost track and you had to move to the innermost track, or vice versa. If the arm started on the innermost track and you had to move all the way to the outermost track. Now, it tells us there are 50,000 tracks, but to move from the innermost to the outermost, you're only actually moving 49,999 times. So you take the total number of tracks and then you subtract 1, all right? Because you're only to move from the innermost to outermost, it's going to be 1 less than the number of tracks. You know, imagine something smaller where there's only 5 tracks. To move from track 1 to 5, you're actually only moving 4 times. All right, so that's the number of times we need to move. The problem tells us that it takes 0.01 milliseconds per move. So we're just going to multiply the number of moves times the time for each move. All right, and that's going to end up with 499.99 milliseconds. All right, worst case scenario there. Now, worst case scenario for latency is that the disk is just a little bit past the start of the sector. So worst case scenario is a full rotation. And with a full rotation, we already know that that takes 8.33 milliseconds. And then the nice thing is the transfer time doesn't change across best, worst, and average. So we know that that's just going to be the same 0.0128 milliseconds that we already calculated. Right. So once we have those numbers, then we just have to go and add them up. So we've got 499.99 plus 8.33 plus 0.0128. All right, and that's going to give us 508.3328. All right, and again, the test will tell you what to actually round these things to. So you don't have to worry about that right now, but on the test, it'll tell you either hundredths or thousandths or whatever. All right, average case scenario, because neither of these are very realistic. It's never very realistic that you're going to have everything lined up perfectly. And it's equally unrealistic that it's going to be the exact worst case scenario. So on average, the seek time requires you to move across 1/3 of the tracks. All right, and the reason it's 1/3 is because the arm can move forward and back. So it ends up being less than like 50% of the tracks because you can always move forward and back, which gets you to things a little quicker. So what we do is we say, all right, there's 50,000 tracks. And on average, we have to move over 1/3 of them. All right. And then we know that each one we move over takes 0.01 milliseconds. All right. So then it just becomes calculator work. 50,000 times 1/3 times 0.01. And we end up with 166.67, we'll say. All right, so that's the average seek time. Now, latency, the disks only spin in one direction. So this case, average will be half a rotation. All right, and again, the fact that this arm can move both up and down is why it's only 1/3, whereas the disk only spins in one direction. So the average spin is half a rotation. So we're just going to take that 8.33 and divide it or multiply it by 1/2 or divide it by 2, whichever way you like thinking about it. Doesn't really matter, but 8.33 times 0.5 is going to be 4.165. 4.165 milliseconds. Again, the transfer time doesn't change no matter what scenario you're looking at. So that's still 0.0128 milliseconds. And then we can just take these three pieces and add them together. So 166.67 plus 4.165 plus 0.0128 gives us 170.8478 milliseconds. And again, you might have slightly different answers depending on your rounding. I'm not really worried about that as long as you're doing the calculations and understand the concept. I'm not going to get too hung up on the rounding as long as you rounded correctly. All right. So guarantee you will see one of those problems on your test. So just make sure that you're comfortable doing those. All right. Last but not least, if the average song takes 5 megabytes of memory, what is the largest number of songs that can fit on a 32 gigabyte flash drive? Show your work. All right, so first things first, we want to convert this over so that we can get it in terms of megabytes. So it tells us that it's a 32 gigabyte hard drive. Oops. All right. And we know that there are 1,024 megabytes in 1 gigabyte. So if we multiply those together, that tells us that a 32 gigabyte flash drive really has 32,768 megabytes. Right, so that's the total number of megabytes on a 32 gigabyte flash drive. If a song takes up 5 megabytes of memory, all right, we can do this 32,768 divided by 5. All right, 32,768 divided by 5. That's going to tell us how many songs can fit on the hard drive. So we're going to take this 32,768. We're going to divide by 5. That's going to give us 6,553.6. All right, but that 0.6 doesn't really help us. We can't round up because we are out of space. So we have to round down in this scenario and just say that we can store 6,553 songs. All right, we don't get to round up here because we're short on space. All right, this is the space that we have. This little bit of space is just going to be wasted. We can't fit a song onto there because there's not enough room. All right, so again, just another question of being able to convert between gigabytes, megabytes, and use those numbers to answer different questions. All right. So if you can do this sort of stuff and you are familiar with the vocab that goes with this unit, so seek time, latency, transfer, primary memory, secondary memory, the different logic gates, circuits, stuff like that, you should be in good shape for that part of the test. And then as usual, the second part will focus on Python and programming and stuff like that. But you have practice materials for that as well. All right, so I hope this was useful. Let me know if you have any questions.